So we're going off script here and bringing in something unexpected. I have posted the PDF for this section. It's a whole new module, but this is a really important concept. We are not going to do the whole chapter, just a few parts. There will be two presentations. The first will be on concentration and the second will be on dilution. So this is chapter 15, solutions. Again, we are only doing a very small part of this. We elected to bring in this topic and minimize some of the other topics because we think this is really important to learn, and we know that we can cut back on some of the other things without you losing anything in the process. Before we begin discussing solution concentrations, let's review what a solution actually is. A solution consists of two parts, a solvent, which is the substance that's present in the largest amount, and a solute, which is the substance that is being dissolved in the solvent to form the solution. For most of the solutions we work with, water is the solvent, so we call those aqueous solutions, and we've been using that AQ as a phase, which tells us that we're working with things that are dissolved in water. And although we usually think of solutions as being liquid, solutions can be gases or solids. Air, which contains many different types of molecules, is a solution. Nitrogen is the most abundant part of air, so it would be the solvent. But for this discussion, we are going to be using water-based solutions for this lesson. A few weeks ago, before we were on this shutdown, we did a lab. One lab group got to do the lab, the other didn't, on soluble and insoluble salts. And we discussed, when we talked about solubility rules, that sometimes combinations of ions will form a precipitate in aqueous solution because water is not able to dissolve that particular compound. We talked about what unsoluble or insoluble really means, and it just means that we have exceeded the limits of water to dissolve something. So solubility is really different for every compound, and in the lab we kind of did an experiment to show that. So what solubility really means, it's a measure of how much of something can be dissolved in a specific amount of water. If you add too much of any solute, there'll be a point where it won't dissolve anymore because basically the water has become full or saturated with that solute. So a solution that is a saturated solution basically contains as much solute as can be dissolved at a particular temperature. So if we add even a little bit more solute, it's going to fall to the bottom of the container. It's not going to dissolve. So it's going to look insoluble, even though it might have been plenty soluble, you just went too far. If something is unsaturated, that means it hasn't reached the limit, so we can add more solute and continue to dissolve it. And to get the concept of saturation, think of a sponge. A sponge will absorb water, and it will get to a point where it can't absorb any more water, and then it drips because the sponge is basically saturated with water. Well, we're now thinking about water being saturated with something else. So saturated basically just means it's full. It can't hold anything else. So we can describe solution concentrations in general terms like dilute and concentrated. All solutions are mixtures. They are homogeneous mixtures, which means that we don't see the parts. And if there is a large amount of solute dissolved, we can call that a concentrated solution. A smaller amount means that the solution is more dilute. Think about making a powdered drink. If you add a lot, then the solution would be concentrated and the taste would be strong. If you add less, then the solution will be dilute and it will taste kind of weak. And we talk about strong coffee and weak coffee, it's the same kind of thing. Something that's watery, which means that it's just dilute. It doesn't have a lot of dissolved solute. So in chemistry and in science in general, we want a more quantitative way to describe concentrations, and there are many different ways to do this. A few weeks ago, we looked at IV bags in the lab, and one of the bags that we looked at was 0.9% sodium chloride, and we called that normal saline. That 0.9% is a concentration. It means that there are 0.9 grams of sodium chloride in every 100 milliliters of the solution. That is one way to measure concentration. In science, though, the most common way to measure concentration is using a unit that is called molarity, M-O-L-A-R-I-T-Y, molarity, and we abbreviate that with a capital M. Molarity is defined as the moles of solute divided by the liters of solution to give the units of moles per 1 liter. It is a concentration. The higher the molarity, the more solute is dissolved. Molarity is a very useful unit, and it can be used as a conversion factor, although we are not going to do that this semester. We are going to learn the basics of molarity calculations. In this very simple example, the solution contains 6 moles of HCl and has a total solution volume of 2 liters. 6 divided by 2 gives a molarity of 3 molar. Remember, big M, or molar, means moles of solute per liter of solution. This doesn't have any sig figs. This is just an easy example. In this exercise, we will find the molarity of a sugar solution that contains 1.00 moles of sugar in a total volume of 125 milliliters of solution. Since molarity is calculated as moles per liter, the first thing we have to do is convert the volume from milliliters into liters. So you'll recall from our first chapter that there are 1,000 milliliters in a liter, so we can set up the conversion. So when we take 125 milliliters and we multiply it by our conversion factor, which is equals 1,000 milliliters, we can cancel out our milliliters, and that leaves us with the unit of liter, and that's what we have in the answer. So 125 milliliters is equal to 0.0 liters. If we then take 1 mole, 1.00 mole, and divide it by the volume in liters of 0.125, we end up with 8.00 molar. And this is 3 significant figures. Don't worry too much about the sig figs. We are going to be pretty lenient. Make sure to always have at least 3 sig figs, and then you'll be fine. However, we don't use scales and balances that weigh in moles, so we need to figure out how to do this when we have a mass measurement. So since we usually measure the amount of substances in mass, or since we always measure the amount of substances in mass, we need to first be able to convert mass to moles before we can calculate molarity. In the last unit, we learned how to convert between mass and moles using molar mass. So once we do that, we can set up our molarity relationship. In this problem, we are going to calculate the molarity of a solution that is made by dissolving 100 grams of NaCl in 1.00 liter of total solution volume. So in order to do this, we first have to figure out how many moles of sodium chloride we have. And in order to do that, we have to convert grams to moles. And in order to do that, we need to find the molar mass of sodium chloride. So the first step is to find the molar mass of sodium chloride. NaCl contains 1 sodium, which has a mass of 22.99 grams per mole, and 1 chlorine, which has a mass of 35.45 grams per mole, which gives us a total molar mass of 58.44 grams per mole. Now we can use the molar mass of sodium chloride to convert grams to moles. The starting mass of sodium chloride was 100 grams, and the molar mass of sodium chloride was 58.44 grams. So we see we put the moles on top and the mass on the bottom so that when we do our math, the grams will divide out. So we're left with moles. And when we convert 100 grams into moles, we get 1.71 moles of sodium chloride. And now finally, we can set up our molarity relationship. So from the problem on the previous slide, we know that the volume of the solution was 2.00 liters. We now have the moles of 1.71 moles. This is just a dash, not a minus sign. 1.71 moles divided by 2.00 liters gives us a molarity of 0.855 molar. And this is 3 significant figures, which is all you need to worry about for these problems. Here's another example with a slightly more complicated molar mass. In this problem, we have a 500.0 gram sample of potassium phosphate, and this is dissolved in enough water to make 1.5 liters of solution. And we are being asked to calculate the molarity of the solution. So again, we have mass and we have volume, but we need moles and volume. So the first thing we need to do is figure out how many moles of potassium phosphate are contained in 500.0 grams of potassium phosphate. Potassium phosphate has the formula of K3PO4. So the molar mass calculation would be 3 times the mass of potassium, which gives us 117.3, 1 times the mass of phosphorus, which is 30.97, and 4 times the mass of oxygen, which is 64, 4 times 16. When we sum that all together, we get a total molar mass for K3PO4 of 212.27 grams per mole. The next step is to convert the mass of K3PO4 to moles. So once again, we have the starting mass of 500 and we have the molar mass of 1 mole equals 212.27 grams. So once again, grams divide away, and we end up with 2.355 moles of K3PO4. Now in this problem, we have 4 significant figures. But in the last step of this problem, we end up with 3. So don't worry too much about 3 versus 4. Finally, we can calculate the molarity by taking the moles that we have calculated as 2.355 and divide it by the volume that was given in the problem of 1.50. And when we do that math, we end up with a molarity of 1.57 molar, or 1.57 moles per liter. So consider separate solutions of sodium hydroxide and KCl that are each made by dissolving 100 grams of the solute in 250 milliliters of solution. Calculate the concentration of each solution in units of molarity. So you should try to do these problems. They will be explained on an EduCreations video that you can refer to. But remember, the first thing you need to do is take 100 grams of either NaOH or KCl. It's 2 separate problems. Convert this to moles. Don't forget to convert milliliters to liters, and then take the moles, divide by the liters, and get the concentration. Now, these 2 compounds are going to have different molarities. It's the same mass, but remember, the molar mass for these is going to be different, so they'll each be a different number of moles. To make sure that you have this concept clear in your head, I want to walk through this slide. Consider that you have 2 solutions of hydrochloric acid, solution A and solution B. Solution A has a greater concentration than solution B. Which of the following statements is true? So let's just say, because I think it's easier to think of it with numbers, let's say solution A has a concentration, even though it's going to be terrible, 2 molar. So we're going to put 2.0 molar. And let's say solution B is 1 molar. And it doesn't matter about significant figures. So we'll just say solution A is 2 molar and solution B is 1 molar. So if you have the same volume, let's say we have a liter of each. If solution A is more concentrated than solution B, if you have equal volumes, then you have more moles of hydrochloric acid in the more concentrated solution. So A is clearly wrong. Solution A will have more moles than solution B. So let's look at number 2, letter B. If you have equal moles of hydrochloric acid in both solutions, then you must have a greater volume of solution B. Well, let's think about that. If solution A and solution B, you have a sample of each, and they have an equal number of moles, but solution A is twice as concentrated. In order to have the same number of moles in solution B, you would need to have a larger volume, because remember, it's spread out in a bigger volume. So B looks like it could be the right answer. But let's keep looking. Letter C says, to obtain equal concentrations of both solutions, you must add some water to solution B. Well, that makes no sense at all, because solution A is more concentrated. So if you add water to solution B, you're just going to dilute it even more. And then the last one, to make both solutions less concentrated, you must add more moles of HCl. Well, that's not right either, because if you add more HCl to the solution, it's going to get more concentrated, not less concentrated. So the correct answer here is letter B, which is indicated. So that is the end of this presentation. When you are ready, do a few practice problems to make sure you understand molarity, then watch the EduCreations video of the demonstrations, and then you can move on to the much shorter video on dilution.